Hey guys, it's Coit back in the lab today. Haven't done videos in a while, so I would figure I have a new project going on. Figured I'd start a series of videos on building a demonstration IEC fusion reactor kind of from scratch. So if you don't know what that is, I will have some other videos explaining what an internal electrostatic confinement fusion reactor is and does and how it works. But this video, I'm going to jump right in as part one on the build of a high voltage power supply system. So IEC fusors need 10 to 20,000 volts, really DC, negative high voltage for demonstration, really to ignite the plasma in them. And that's most demo fusors you see at universities or that other people have built kind of are in that range. If you're going to do actual fusion with them, really make neutrons and do the real fusion process, you need 40, 50 or higher 1,000 volts in your fusor to really make a working system. So we're going to do both. We're going to kind of start in increments. We're going to do some demonstration fusion, and then we're going to do real fusion and actually make some radioactivity. So I want to build a power supply that can do both of those things. And many ways to build a power supply for this kind of fusion reactor, but I am going to be working with this X-ray transformer. So there's a whole list of pros and cons of various transformers that you might see designs for online, such as neon sign transformers or even microwave oven transformers, but all of those other transformers are really not suitable for the higher power levels and higher voltages we need to achieve. An X-ray transformer is. These things are designed to make 50 to 100,000 volts for powering an X-ray tube for dental units or the doctor's office or whatever. So this is a very old unit. This is an iron core X-ray transformer that will take in 120 volts alternating current and step it up to 100,000 volts. It has a bunch of different windings on this core. So I got this unit off eBay with no diagram or anything, so I wanted to do a little video of how we start to analyze this transformer, figure out what has to be wired where, and also the overall design of my power supply, because we need to be controlling the power going into this transformer to limit the amount of current it draws. We need to be controlling the output voltage of it, and we need some very specific parameters. We need negative high voltage output in relation to our grounded DC, because the outside of our fusion chamber is going to be ground and the grid internal is going to be at a negative 50,000 volt potential. So I'm going to show you how to do that and how we're going to wire this guy up in that configuration. Okay, so step one, we need to understand what we're trying to achieve in terms of the overall power supply design for the fusion reactor. So here is a rough schematic. This is hand drawn, of course, right now. So I'll walk through this real fast. Right here, this component here you see is our X-ray transformer. So you will have a primary winding which will accept 120 volts AC input. And then we're hoping to find two secondary coils on that X-ray transformer, each making about 50,000 volts. You can look at a bunch of different designs for these X-ray transformers on the internet, and you can kind of get a feel for how most should be wired internally. So we're also expecting a couple other windings to be on this secondary to do things like metering, and you can see I'm going to meter my entire system but separately from the built-in metering coils within this X-ray transformer. But regardless, we're really focusing on finding the two 50,000 volt coils, because we're going to use them in this kind of circuit here with diodes in this orientation to effectively parallel those two 50,000 volt windings and rectify them to make a negative 0 to 50,000 volt output down here. This will allow us to tie that center tap between those two coils to the core of the transformer and use that as our ground for the fusion reactor enclosure. So really, you could think of this as just this is just a voltage potential here. So you can almost think of this as being the positive output, but we're tying that to our ground so that we can ground the outside of the chamber itself and not hurt anything, and we'll be feeding the internal grid a negative 50,000 volt potential. And again, you can see how we're going to do some kind of metering strategy here. We're going to be measuring the milliamps, because this should be able to make 0 to maybe 30 milliamps total into our fusor, and then 0 to negative 50,000 volts. We'll have a voltage divider here, which will allow us to use a much lower voltage, of course, meter to measure that. Now, one thing to note also about these X-ray transformers is they are not current limited. So they have no internal ballasting or really current limit, and will very much so draw as much power as they feel like they want, depending on what you have connected to the output and how it's hooked up. So we will have to do that ourselves, and there's two strategies to do that also. I can put an inductor here that will limit, basically create an impedance. You can think of that as like a complex resistance here in series with the primary, and that will allow us to limit the current going into the overall system. A lot of people use a shorted secondary on a microwave oven transformer, and they literally just run the microwave oven transformer primary in series here and just turn it into an inductor effectively. I'm probably going to use a more complicated approach, which will be to have a solid state relay synced to the AC line input, and that'll allow us to do almost effectively a light dimmer switch. It'll allow us to clip the AC wave coming into this system and overall limit the current it's drawing. But we'll see when we get there what we decide to do. This video is really about what this design looks like, and then how we actually go from in state, which is this, and start with just a raw transformer we bought off eBay. So let's take a look at this transformer now. I'm going to switch over to that. Now, I just found this transformer on eBay listed as an X-ray transformer, 100,000 volt input, with no other details. So this is literally, it showed up in a box just like you see it here, and I'm going to pick it up and show you all the different wiring. So we've got 3 wires here. Don't know what those are. So we're going to assume I have no idea what any of these windings are and show you. So there's 3 wires here, there's 2 wires here, there's a center tap wire connected down going into the transformer there, and then on the other side we've got 3 more connections. This guy and then these 2. So most designs should be simple to understand. If you look online, X-ray transformers have like 4 or 5 wires, connections coming out of them. This one has 9. So how do you start with something with 9 connections going to places where you really can't tell what they're going to? How do you determine what that's internally wired? So to do that, we start with a process of measuring resistance of all the windings. And I'm going to show you how I did this, but I did a little bit of a cheat first. I already know these 2 thick wires here coming out at the base here are going to be my primary coil. I know that because I did some initial checking with a multimeter and determined that this was a very low resistance, a couple ohms, and it's the thickest wires coming out of this unit, and I know that that is most likely, and it's not connected to anything else, so I know that these 2 wires are most likely our primary coil. That is the only thing I know. The other 7 connections on this transformer, we have to map out and figure out what the internal structure is. Here's how I did that. I did the resistive process, and I started by labeling every one of my connection points so I knew what was labeled where. So I took a Sharpie and just wrote A, B, C, D, E, F, G on each of those terminals. Next, I made a little matrix here, and I checked the resistance between every combination of connection points. And we know that the transformer, the testing of this is pretty much symmetric, so you can effectively eliminate half of this graph you see. And now we know that all of our connections are mapped appropriately. So from terminal A to terminal B we had infinity ohms, so no connection. A to C we had no connection, but B to C here we have a short, 0 ohms. D to A we have 0 ohms. B to D we have no connection, and onward. So you can go through the entire process to do this, and you get some really interesting results. For instance, this last ground connection, so the G connection is that center tap wire on this side. If you measure it to the other terminals, G to A is 71.8 ohms. No connection to B, no connection to C. G to D is also 71.6 ohms. No connection to E or F. So once you have this map, you can go back and write down the things that were important. And that's what we have here. So based on the last table you just saw, I found that B and C were shorted, D and A were shorted, E to F was 60.1 k ohms, no other connections to anything else. The G with the center tap had connections to both A and D, each at about 71 ohms each. So from this data, we can extrapolate, combined with some kind of an intuition, I guess you would say, on how this thing could be wired internally, and I came up with this design. We know our two primary inputs. We know that E to F up here is a separate winding, so that's probably one of the high voltage windings here, not connected to anything else. B and C were shorted, don't appear to be connected to anything else. The resistance was very low, not 0.05 ohms. Then we had this 71 ohm winding here, and A and D are both shorted, and this G was a center tap, which means it's connected to the core. So this is, I believe, the wiring diagram for inside this transformer. Now we're going to go to part 2, and I'm going to talk about how we actually can verify this by injecting a signal into the transformer, and we can figure out the phasing of these windings, and we can figure out the exact ratio of these windings, and we will be able to extrapolate exactly how much voltage we'll get. Okay, so part 2 here, we are going to verify our internal wiring of this transformer by actually injecting it with a small signal and measuring through the transformer action the output voltages, and really see them on the oscilloscope to verify proper operation, our ratios, and our phasings of this transformer. So I'm going to describe what I have set up here. Up on top, I have an oscilloscope and a signal generator. So the first thing we're going to do is we're going to use the signal generator to inject a very small, probably about a 1 volt peak-to-peak signal into the primary of the transformer. Now, remember, this transformer is extremely high voltage. It's meant to make 50,000 volts with a 120 volt input. So you can't put 120 volts into this on the primary and make that full amount of voltage without this being submerged in oil. It will destroy the transformer completely. And we're not quite there to packaging this transformer yet. So in this case, even a 1 volt signal coming out of the little signal generator up here will still make several hundred volts on the secondary output of this transformer, just because it's such a high voltage transformer. So what we're going to do is we're going to measure the output of the signal generator on the oscilloscope here directly on the primary input, which is what you see right here. So we're going to change some settings here to make this look good, so bear with me for a second. Okay, so far I have changed the signal generator and the oscilloscope, so we are measuring the output directly at 1 volt peak to peak on the oscilloscope. Sorry for my oscilloscope scanning here in the video. And then I set the frequency to be exactly 60 hertz, so that we are feeding the transformer the frequency that it is going to eventually operate at. Then we have a second probe here connected to channel 2, which I'm going to enable, which is connected as a 10x probe. Remember, high voltage is going to come out of the secondary of this transformer. Not enough to hurt anything, because we're only injecting 1 volt with a very low power signal generator, but enough that it's still going to make a high voltage signal. So I have a 10x probe, which has a 10x resistor divider effectively in it, and I have the oscilloscope set up for this 10x probe, and it's on something like 50 volts per division on the second channel here. So we should be able to see several hundred volts worth of range on the oscilloscope on the output of this transformer. So I'm going to switch back and show how we're wiring the transformer. You can see that we've got the signal coming from the signal generator into those 2 primary wires I told you about, and directly in parallel with that we have the channel 1 of that oscilloscope probing, and then I have the 10x probe with channel 2 ready to probe the transformer over here. So remembering our schematic up here, we've got this side set up. We need to test each one of these windings the way I have drawn it on the schematic and see what we actually get output with the 1 volt input. So I'm going to start by connecting the ground point we had originally to terminals A and D, because we think that is one of our high voltage windings based on our initial analysis. So I'm going to connect the ground of the probe to our center tap there, and then I'm going to connect this probe connection to A or D, it doesn't really matter. So I'm just going to connect to A, which is right here. All right, let's see what our oscilloscope is telling us now. Hey, look at that. We have a signal here, and it is obviously much larger than the input signal. Remember, one is measuring at 50 millivolts per division here, which is the small signal. One is 50 volts per division. So our channel 2 is at 228 volts right now with a 625 millivolt input signal. Now, I had set that to 1 volt input before, and it actually dropped a little. That's because once I connected everything to this transformer, it's actually pulling too much power from the signal generator and dropping that voltage. So I'm going to compensate the output of the WaveTech here until it's outputting 1 volt into that transformer again, and we're going to see what that ultimate final result on the secondary output of the transformer is. So we're going to turn this output up until we get a volt going into the primary, so we have an easy ratio to work with. Right, perfect. 1 volt exactly right here. So the scope is seeing 1 volt on the input. Our output voltage of one of those 50,000 volt secondaries is 356 volts. Which is fantastic, because that means with 120 volt input, we are going to get right around 50,000 volts output, which means that is definitely one of our secondaries. And you can see the way this is wired currently, these two signals are in phase. They're overlapping properly. That means that the windings, a normal transformer, the way it is winded, if you put a signal into it, it will create a 180-degree phase shift on the output. That means we actually have them in phase right now, so we've wired the connection to the secondary kind of in reverse right now. But that's fine. We just need to make a note of this, and I want to know this because when I combine the two high voltage secondary windings in parallel, they have to be in phase with each other. If they're not, the signal will cancel itself out and I will get no voltage on the output of the connection. And you can see in our diagram, I'll pull the notebook up here, you can see I've already done this process, and I know the phasing based on the way I've labeled everything. These little circles on the transformer indicate the phasing. So when I put these two windings, which are our two high voltage windings, I'm not going to go through the whole rest of the process, but you can see how to measure the output through this process. When I go to combine these two high voltage windings in parallel, as per the original schematic, I need to connect F terminal over to our ground connection here, so that this phase dot kind of goes in series with the part of the winding up here that does not have the dot on it. They need to kind of be in, you can't connect, if I connect this phase dot to the same terminal of this winding's phase up here, you're going to get the cancellation because they're going to be out of phase with each other, and you're just not going to get any power. So I can wire that up and show you, but I think this makes enough sense that we will move forward. And I will just complete by telling you that these two windings are high voltage winding, and when I do this, connect this F to the ground system here, I get the proper amount of, I get 100,000 volts when I put them in series like that. Again, I'm not going to be putting them in series, I'll be putting them in parallel, but this verifies the proper operation and tells us that this entire diagram here is working properly. I checked the same way, B and C and A and D directly, and I verified these are shorts. They are not, do not appear to be windings. They're not really making any power. Maybe a very, very small voltage if I zoomed into the scope. Could be for some very low power metering, but right now we're not going to worry about those. But that's basically it. So what's the next step with this transformer? We have verified our system, how it's wired. We know exactly how it's wired, that it's making the right voltage ratio. The next steps to build the actual FUSOR power supply is to build an enclosure for this unit, get it submerged in some oil, because this thing cannot run at anywhere close to full power unless it's under oil. So I need to get a plastic container of some sort, fill it with mineral oil, probably pull a vacuum for a little bit on that container to suck all the air bubbles out of the internal windings of this, because this needs to be saturated internally with oil. And then we're going to build the rest of that circuit out. So I haven't done that yet, but I got started. These are my high voltage diodes. So I pulled these little tiny diodes in here off of a other high frequency voltage multiplier board that I had laying around. Each of these diodes are rated for 20,000 volts at 100 milliamps. So this is a pretty beefy diode stack. I did 6 in series, so 120,000 volt rated diode stack at 300 milliamps is the datasheet spec for this diode stack. I wouldn't trust it that much. That's why it's colossally overbuilt for this application. But hopefully this works well. And I have 2 of them because you need 2 of them as per the original schematic for the overall power supply. So we're going to get all of this submerged in oil and wired up in a different video and verify the final power supply operation. Thank you. Have a nice day.